Welcome, everybody. This is Professor Dan at CU Boulder, and today we are going to be talking shear and moment diagrams. Now, we're going to talk the graphical and show you where we can use a graphical method, but also use like what's also known as our equation method. And so the fundamental aspect of it that we've learned is that our change in shear is equal to the integral of our loading dx, and our change in moment is equal to the integral of our shear dx. Know that the integrals are areas. Integrals give us the area under curves. And so one of the things I want to make sure that we see is when we have an applied loading, when we take the integral of that, we often will come up with a straight line, a constant. And we take the integral of a straight line, we get, or a flat line, we get a straight line that's often increasing or decreasing. When we take the integral of a line, we often get a squared term, and we take the integral of a squared term, we often get a cubic term. And so, yeah, this is constant. This is x squared, and that is x cubed. And so before a constant, we often will have this discontinuity. All right, so let's see how this applies to our shear and moment diagrams. Well, when we look at our first beam, we have this beam with some force. It's as if somebody weighing 27 kilonewtons, that's a big person. It's a thing, let's say it's a rock, at on a beam that's 9 meters, standing 6 meters away from reaction A. And so by this point in time, I'm assuming you know rigid body equilibrium. So we're showing that f of x is 0, f of y is 0, and we can take the moments about anything, but if we take them about point A, we can solve for our reaction at by, which is a roller. And so we find ay is 9 kilonewtons and by is 18 kilonewtons. So when we go to our discontinuity, when we have applied load, that is a discontinuity. So at the start, we go from 0 up to 9 kilonewtons. We stay at 9 kilonewtons for our shear force right up until the 27 kilonewtons is applied, and that is applied downward. So we go down, we start at 9, we subtract off 27, and we go down to 18 kilonewtons, and it's negative. And we stay at negative 18 kilonewtons until we hit by, which brings us back up to 0. And we always want to start and end at 0 because this is a statics problem. We want to make sure that we're not moving. All right, so that's what our shear diagram looks like. And if we want to, we can plug in that that's 6 and that's 3 meters. And what we say is the change in shear, we take a discontinuity and it kind of becomes a constant. So we have a discontinuity AY, we go up to 9, we stay at 9 until we have a discontinuity in force, and then we go down. And then we stay at that minus 18 until we have our final discontinuity in force, BY, and that goes straight up. Now we say that our constants become line. Let's see how that works. So when we have our change in M, that's the integral of our shear diagram dx, and our integral is just the area under our shear diagram. So our first moment is 0. We don't have any applied moments. There's no discontinuities at a pin reaction. There's no moments there. And we go up to a certain number. We know it's a straight line. So what is that number? That number is the area under our first curve. It's a positive area. It's above the x-axis. It's 9 times 6, so it's 54 kilonewton meters. And then we have a negative area that we add to this. Well, it's minus 18 times 3. Minus 18 times 3 is minus 54 kilonewton meters. And so we just come back down. So we can start to see how we have our discontinuity. When we integrate that, we see some constants, some straight lines. When we integrate those, we start to see some slopes. Okay, when we integrate those, we're expecting to see some squared terms and then cubic terms. All right, so let's try it out. All right, so now instead of applying a point load, let's apply a distributed load. So it's 3 kilonewtons per meter times 9 meters. So how many total? We want to get our resultant force, and we know that our resultant force, FR, is 9 times 3, which is 27 kilonewton, and it's applied at 4.5. So when we solve our reaction forces, we solve our AYs and BYs, we see that it's evenly split, but you can follow this along as rigid body equilibrium. So we see at the start, our AY is 13.5 and our BY is 13.5 at the end. So what happens in between? Well, now we have this distributed load. And so our distributed load is flat. And so we see a flat load is likely going to become a line that isn't flat. And so what does our V look like? Well, we start not at 0. AY, we start at 0 and we go up to 13.5. And then we say we go down linearly till we hit BY, and we're expecting this to be minus 13.5. Because BY is 13.5, it brings us back to 0. So let's see, does it work? Well, if AY is 13.5, we have 9 times 4.5. Oh, nope, not 9. 3 kilonewtons per meter times 4.5, and it's negative because it's going down, equals minus 13.5. So at 4.5, we have 13.5 minus 13.5. So that is 0. And why that's important, because our 0 for our shear is going to be our maximum for our moment. So we look up and we say, how does moment look? Well, moment is the shear, is the integral of shear. So we look down and we say, oh, moment's the integral of shear. And we know that that is our maximum. We know that we start at 0 with our moment. And so we know that its shape is going to be an x squared term. And so we go up because we have some positive, and then we go down because we have some negative area. And then when we have the area of a triangle, it's 1/2 base, which is 4.5, times height, which is 13.5. So we do that out. And we see, so if we take 4.5 times 13.5 divided by 2, that's 30.375 kilonewton meters. All right, so that's how we can do this graphically, but does the math work? Well, let's see. So if we have, our function W of x equals 3 kilonewton per meter, it's acting down, so that's minus 3 kilonewton per meter. We take the integral of that dx, we get minus 3x times, minus 3x plus c. Minus 3x plus c. What is our initial condition? Well, we know at 0, we're at 13.5 minus 3x plus 13.5. All right, when does this equal 0? So we know shear is equal to that. Shear equals 0 when minus 3x plus 13.5 equals 0. 13.5 divided by 3 is 4.5. So things are pretty consistent. We take the integral of shear, integral of minus 3x plus 13.5 dx, and we know that that's our change in moment. So that's minus 3/2 x squared plus 13.5 x plus c. Our moment starts at 0. So we want to check it. Does minus 3/2 x squared plus 13.5 x, is it maximum at 4.5? Well, let's try it. Minus 3/2 times 4.5 squared plus 13.5 times 4.5. minus 3 divided by 2 times 4.5 squared plus 13.5 times 4.5. That's equal to 30.375 kilonewton meters. So we see that it's consistent whether we use the graphical method or we use these equations. All right, so now let's talk about our final example. So this final example is we have a loading that is linear going up. So we start with this one. We start with our x term. All right, so how does this work? Well, again, the first thing we do is solve for our resultants. So our resultant is the area under the curve. So 6 times 9 divided by 2. That's 27 kilonewtons. And we know that it acts a third of the way from what I call the heavy end of the triangle. Okay, so we do our analysis and we see that actually the resultant forces or our reaction forces, AY and BY, are similar to our first example. Oh, that's nice. So when we start our analysis, we know that we start at 9 kilonewtons for our shear. Let me zoom in a little bit. So we start with 9 kilonewtons for our shear. And we're saying that we're going to go from a line to a squared term. All right. And so we also know that our loading is down. So we're going to have a decreasing squared. And it goes down to what? Well, we know BY is 18. So let me just clear out a little space here so we don't get confused. We know we go up 18 at the very end. So we know we got to end up at minus 18 right before then. So the question is, where do we cross over? Well, that is a little bit harder this time. So the first thing we have to do is figure out our loading equation. So if we're at 6 kilonewtons at 9 meters and 0 at 0, we can use our equation for a line, y equals mx plus b. B is 0 because our y-intercept is 0, and our slope is 6 divided by 9. We're at 6 at 0.9, and rise over run, that's 6/9, but we're acting down, so we're at minus 6/9. So our slope is minus 6/9, and our equation is y equals minus 6/9 x. All right, we say that shear is the integral. The change in shear is the integral of our loading minus 6/9 x dx. So 6/9 is minus 2/3. Take the integral of minus 2/3 x dx. Delta V is minus 2/3 x squared over 2 plus c. What is our initial condition? Well, we were at 9 kilonewtons at 0, so it's minus x squared over 3 plus 9. Okay. Our engineering question is, what is or where on the beam does our shear equal 0? Well, set our shear equal to 0. X squared over 3 plus 9 equals 0. Bring our x squared to the other term. 9 equals x squared over 3. 27 equals x squared. Take the root of both sides. We only care about the positive root, so 5.20 equals x. That's our crossover point. Now our graphical said we go from a line, we take the integral, we get x squared. We saw that. We took the integral, we got x squared. We take the integral again, we're going to get a cubic term. So we're going to add this positive area, subtract off this negative area. It's got to equal 0 because we have no applied moments at the endpoints, and we know we have to close our shear and moment diagram. So our moment, we go up as a cubic and then come down to 0. And so what is our maximum? Well, if we integrate, so the change in moment is the integral of v dx. We know moment is, or we know shear is minus x squared over 2 plus 9 dx. Take the integral of that, and we get minus x cubed that should be a 3, minus x cubed over 3 times 3 plus 9x plus c. See, what are our initial conditions? Our initial conditions are 0. We don't have any applied moment, so that goes to 0. And so we have our equation for moment. All right, so what is our maximum moment? We just plug in our 5.2 into our x. Moment equals minus 5.2 x, or 5.2 cubed divided by 9 plus 9 times 5.2. So 5.2 cubed divided by 9 negative plus 9 times 5.2, and I see 31.2. So we know it's 31.2 kilonewton meters. And there we go. So we see that this graphical method, and there's some common themes that we can apply throughout our shear and moment diagrams. So I hope that this helps. And in the next video, we'll show how to combine a point load with a distributed load. All right, thank you.